Hello everyone, welcome back. We will get started into Unit 1 Kinematics of AP Physics 1 review. This is the very first unit. It is the most basic. It covers the foundation of what classical mechanics is. So let's get started. Before we get into actual any mechanics and equations and variables and stuff, we must first understand what scalars and vectors in one dimension are. To understand all variables and quantities in this course, we must discuss these two things. Scalars are quantities described by magnitude only, so you can say mass, length, time, energy. These are all just magnitudes, and magnitudes can be represented by a single number or value. So you have 10 kilograms, 5 meters, 15 seconds, right? But vectors are quantities that contain both magnitude and direction. So you have velocity, force, momentum. We will learn this in future topics, but remember how scalars can be represented by just a single value, right? Vectors representing them is much more complex because graphically they are represented as arrows. The length of the arrow represents the magnitude of the vector. The direction of the arrow is the direction of the vector. So we have these two vectors here. I labeled them both vector A. We can see on the one on the right is a larger vector because it has a greater length. One has a greater magnitude. Um, when you try to convert this graphical format into, let's say, an equation or a numerical quantity, we can set the vector into some linear axis. So for example, in this case, I have the Cartesian coordinate system, the x-axis, right? So what we would say is that the vector here, this long vector, is offset by theta degrees, the angle, above the positive x-axis. This is just one example. You will find many more cases throughout physics. And now let's talk about scalar and vector addition. Since scalars only have magnitude, adding scalars is just simple addition. So let's say you add mass, 5 grams plus 5 grams is 10 grams, right? Pretty simple. But vectors include both magnitude and direction, so adding vectors also must consider the direction of both vectors. So let's say you're adding vector A to vector B. The final resultant vector is, remember, tip to tail vector addition. It's the tail of vector A to the tip of vector B. So you have this final vector here, vector A plus B. And this allows us to create a foundation for the rest of kinematics. Kinematics is the study of motion. It represents the position of objects, how fast they travel, and by how much they speed up or slow down. These topics, concepts such as position, velocity, and acceleration describe how objects travel throughout space and time. And to know the other concepts, we must first cover position and displacement. Displacement describes the straight line distance and direction between the final and initial position of an object. So let's say we have a little gray path here, right? This is the path taken by an object. But the displacement is just a straight line distance between the initial and final point. So this white line right here. And since we can literally see it's an arrow right here, right? Displacement is a vector quantity, so we must take into account direction when adding or subtracting displacements. This is just a basic equation. It's more conceptual, but it'll become relevant in future topics. So we can now start talking about velocity. It's the change in displacement of an object over an interval of time. So we have the average velocity equation. You will never have to discuss instantaneous velocity, which is the velocity at an instant at a point in time in AP Physics 1, unless if it's in a qualitative sense. But in quantitative, so equations, you will never be discussed. You will never have instantaneous velocity being discussed. Velocity is different from speed, which is the total distance, the total path traveled over this interval, right? And again, velocity is a vector quantity, so it's important to consider direction when determining the displacement that causes velocity or when adding velocity. This is going to become relevant when you have relative motion. You'll see it in a little bit. So now we have acceleration. It's the change in velocity of an object over an interval of time. So it's a measure of how quickly an object is speeding up or slowing down. And just like other variables, it is a vector quantity. This variable acceleration is going to become pretty important in later topics, but the direction of acceleration must be taken into account for each problem. You will especially need to know this for unit 2, actually all units pretty much. So using these three variables, we can represent motion. The motion of an object can be represented by a few various elements. So we have equations, graphs, figures, descriptions. We can look at these in turn and analyze how the motion of an object can be predicted and calculated. So remember the kinematic variables in their equations. You have the displacement equation, the average velocity, and the average acceleration equations. These aren't the only equations that we can use to define motion. In uniformly accelerated motion, where acceleration is constant, the following four equations can also be used to represent instantaneous linear motion. So instantaneous velocity, not velocity, but instantaneous variables in one dimension. So we have this. We'll get to another one in a bit. But let's first, before we get to anything, let's manipulate a few of these equations. You remember that change in this, no, that change in position, final minus initial, is equal to displacement. So we can manipulate these two equations to get um, these set of equations. These are on the equation sheet, these three, but I highly recommend you memorize them because they will become important pretty later on. And our fourth equation, which is optional, it's not on the equation sheet, is this one right here. Using these four equations, we can establish five variables that are found in these functions, you could say. So we have displacement. Remember, that's why I said to reformat, because this is pretty important here. The displacement, final velocity, initial velocity, acceleration, and change in time. And using these five variables, each equation has a single missing variable. So the first one has no change in displacement, or not change in position, change in position, has no displacement. This one has no final velocity. This one has no change in time, and this one has no acceleration. This equation here actually is usually given the title the no time equation. But if you're given three of the five kinematic variables that are right up here, you can find the other two using a combination of these four UAM, uniformly accelerated motion equations. Now let's go into some graphical representations. We can represent motion graphically. So we have this equation and this equation, the average velocity and the average acceleration equation. By making these equations analogous to slope or area, we can create some relationships. So remember slope and area in geometry and algebra? Slope is the change in the y variable, the change in the function variable over the change in the x variable. And area is just base times height. So let's first discuss slope. So looking at the velocity equation, we can see that um, the average velocity equation can be set in terms of a graph where the y-axis is displacement and the x-axis is the time, right? So this change of position as a function of time, and same with acceleration. Acceleration, for we can create a relationship where um, velocity is a function of time, and you notice the relationship here. In this we can say that the slope of the displacement versus time graph is velocity, and that the slope of a velocity versus time graph is acceleration. Now let's go with area. And area, we can see that we can manipulate these two equations to get position. The change in position as a function of time is the product of average velocity and change in time, and the velocity as a function of time equation is the product of average acceleration and change in time. So relating that back to the area equation, we can see that the area under the curve, the area between the graph, the line, and the x-axis is of a velocity versus time graph is displacement. So the first equation right here. And the area under the curve of an acceleration versus time graph is velocity. So you can find the area under the curve usually it'll usually be a simple trapezoid or square. You can find the area under that curve. If the area under the curve is above the x-axis, then it is positive. If the area is below the x-axis, it is negative. Let's look at some graphs to understand what we mean here. So we have a change in position, sorry, I keep saying displacement, change in position over time graph, and we can see that the position of an object as it changes, the instantaneous velocity is the slope right here, the instantaneous slope. In calculus, in AP Physics C, this is called a derivative. And for a velocity of an object as a function of time graph, we can see that the instantaneous slope, the derivative, is the instantaneous acceleration, and that the area under the curve is the change in position. For a acceleration of an object as a function of time, we don't really have anything for the instantaneous slope. That's not really relevant. Same with the area under the curve of this graph here, but we can see that the area under the curve of an acceleration versus time graph is the change in velocity of an object. It's not the final velocity, it's not the initial velocity, it's just the change in velocity of an object, right? So now let's look at reference frames and relative motion. So the motion of objects around us seem to change depending on our perspective. So when you're in a moving car, let's say your car is moving relatively fast. Um, the motion of other cars that are slower behind you, they seem to go backwards, kind of like this red vector here. It's kind of going backwards relative to you. And now notice these are arrows right here, right? We can see that relative motion is just vector addition. So let's take an example of an observer represented by this black dot and the motion of the boat. So relative to the observer, the boat is moving at this speed, this velocity here. You can indicate it by a subscript with boat dash observer like that, kind of like that. But the velocity of the water is going backwards. So actually, when you think about it, the if the water was still, the boat would be going much faster, right? So we can represent this as vector addition. So if we add the velocity of the boat with respect to the water, which is this top orange vector here. So imagine if the water was still, this is how fast the boat would be moving. And then when you add the vector of the water, that is with respect to the observer right here, with this blue vector here, we get that the velocity of the boat with respect to the observer is this little red vector here. It's vector addition. Now let's say you want to add these two vectors here, right? You want to make them add up to this vector right here. So you would have to, when the one's going in one direction, the other's going the opposite direction, you have to flip one vector. This is vector subtraction. You have to flip it. It's just vector addition. Here you just have to add the negative. So you have to add the reciprocal. That's why the arrow flips here. So yeah. We can continue into two dimensions. So before we get started into two-dimension vectors, we have to first remember when I said that vectors can be set in terms of an axis. We can use that concept to divide vectors into components. So we have a vector here that is divided into its y direction and its x direction. And remember your trigonometric relationships in geometry, the sine of this angle is opposite over hypotenuse. So Vy over V. So it would be established like this. And same with the cosine of the angle here, adjacent over hypotenuse. So it's the x direction of the vector over the vector itself. And when we manipulate the equation around, when we multiply by the denominator, we can see that let's say this is velocity. The velocity in the y direction of an object is equal to the velocity of an object times the sine of the angle theta with respect to, let's say this is the x-axis here. And same thing with the velocity in the x direction. It's the velocity vector times magnitude, you could say, times the cosine of theta. And remember that the Pythagorean theorem, a squared plus b squared is equal to c squared. So when you have the x direction of the velocity vector squared times plus the y direction of the velocity vector squared, you get the vector itself. This is the Pythagorean theorem. You can confirm this if you substitute these two in. It makes sense. All right. So projectile motion is a special case of two-dimensional motion. We can break the kinematic equations into components to help solve for quantities in projectile motion. When an object is in projectile motion, the velocity in the x direction right here is constant. It doesn't change. If there's no air resistance, it doesn't change. If there is air resistance, the velocity in the x direction decreases slowly. On the AP exam, the acceleration in the y direction on Earth is equal to negative little g. Little g is, for the purposes of the AP exam, 10 meters per second squared. That's the acceleration due to gravity. You can use 9.8 or 9.81 meters per second squared, but they will also are also perfectly fine with 10 because that's just an approximation and it makes calculations easier. So let's say you want to find the time it takes to complete this projectile motion here. You can use these two equations, or if you want to find the displacement, you can use this equation to find time. Since we already know the acceleration in the y direction, it's negative little g. We can substitute that in, and then we can substitute it into this equation if we already know the initial velocity vector here, because we know that the x direction velocity vector is always constant. So Thank you for listening. Thank you for watching.